Hello, everyone. We are starting a new semester of combinatorics seminar in New York City at CUNY Graduate Center on Manhattan. And the first speaker today, I'm very glad to bring forward my colleague at Hofstra University, Rowland, and he will be talking about algebraic power series in their arithmetic complexity.
Thank you. So this is work with Manon Stipulanti and Reem Yassawi. Reem is a longtime co-author of mine. So some of the work I'll be talking about was stuff we did almost 10 years ago, and then some of it is much more recent and currently ongoing. So this is motivated by this question, which was the subject of several papers 15 to 20 years ago, which is that if you take a sequence that counts something, so a sequence that arises in combinatorics, and you reduce it modulo a prime or a prime power, what does the sequence look like? So for example, everyone's favorite sequence, the Catalan numbers, counts plane trees with n edges. So a plane tree is a graph with a single root vertex that's placed at the top here. And then every vertex has some number of children, and the children are ordered. So it's sort of fixed in the plane. The ordering of the children determines you could read it sort of left to right. Like this could be the firstborn child of this vertex, and this is the secondborn child. And so if you fix the number of edges in one of these plane trees and count all the possible plane trees with n edges, you get the Catalan numbers. So these are the trees with 4 edges. And there should be 0, 1, 2, 3, 4. There should be 14 of these plane trees, and this is what we see here. So what if we take this integer sequence and we reduce it? We reduce every term modulo 2, for example. So most of the Catalan numbers, it looks like, are even. That's what all these zeros are. Where are the odd ones? They're at position 0, 1, 2, 3, 4, 5, 6, 7. This one's 15. So these are precisely 1 less than a power of 2. So when n plus 1 is a power of 2, you get an odd Catalan number. Otherwise, the nth Catalan number is even. And this is pretty easy to prove because the Catalan numbers have this formula in terms of a binomial coefficient, 2n choose n divided by n plus 1. And a result from Kummer tells you what the highest power of any prime p dividing a general binomial coefficient is. So you can use that to determine when your nth Catalan number will be odd or even. So that's mod 2. What if we include more information by going to the Catalan numbers mod 4? So this is sort of a refinement of the information that's in the Catalan numbers mod 2. So if you project this sequence mod 2, you'll get the sequence we just got back. So the odd Catalan numbers are these ones here, and the even Catalan numbers are now either 2 or 0 mod 4. You'll notice there are no 3s mod 4. So if we took a random integer sequence, we would expect to see some numbers that are 3 mod 4. In fact, there is no Catalan number that's 3 mod 4. And here's a characterization of when the nth Catalan number is 0, 1, or 2. This is from 2008. This is the case we just saw on the previous slide for the Catalan numbers mod 2. And then what determines whether an even Catalan number is 0 or 2 mod 4 is whether n plus 1 has this form. So these are starting to look like, it's starting to look like information about the base 2 expansion of n, or n plus 1 or something. And in that same paper, the same authors also came up with this formula for the nth Catalan number mod 8, which is, again, even more information. It includes all the information mod 4 and includes all the information mod 2. And in particular, no Catalan number is congruent to 7 mod 8, because if it were, then that Catalan number would also be congruent to 3 mod 4. And there are just more cases. And a couple years later, there's a paper that determined the nth Catalan number modulo 16. This involves a bunch of other functions that I'm not going to define, this D and CF2. All these things basically have something to do with the base 2 representation of n. And in the same paper, they also determined the nth Catalan number modulo 64. So one possible career path is, you just keep raising the power of 2, and every few years you just write a new paper about a refinement of the of the Catalan numbers modulo that power of 2. But I want to argue that this is not the right framework for thinking about these sequences, and in particular, this is not the ideal representation of an answer to the question, what is the nth Catalan number modulo a prime power? But let me just mention there are several other sequences that arise in combinatorics whose number theoretic properties were also investigated in a couple of papers. This is the sequence of Motzkin numbers. So these are like a close cousin to the Catalan numbers. They often arise when you have a family of objects that's counted by the Catalan numbers. There's usually some modification that will give you the Motzkin numbers. And the modification in this case is you still count plane trees with n edges, but you restrict every vertex to having at most 2 children. So these trees are excluded because there's a vertex that has 3 or more children in them. These are the trees where each vertex has at most 2 children. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. And the 0, 1, 2, 3, 4th Motzkin number is 9. So here's the Motzkin number sequence modulo 8. And there's a theorem, well, it was originally conjectured by Emmerich Deutsch and Bruce Sagan and Tewodros M. de Berhan that no Motzkin number is congruent to 0 mod 8. And this was proved by the same authors who worked on the Catalan numbers, I think in the same paper. So again, this was 2008. And the Deutsch-Sagan, the Deutsch-Sagan paper was 2006. So, this period from 2006 to 2010, 3 papers appeared about these combinatorial sequences modulo prime powers. Here are just 3 more examples of sequences. This is in the Deutsch-Sagan paper. The first sequence is the number of directed animals. Really, this should be called the number of directed plants, because what you do is you take a square and you put it at the origin, and then what you're allowed to do is grow the animal or the plant either going to the right or up of an existing square. So here you're only allowed 4 squares in this picture. How many different animals or plants can you build with only 4 squares? And there's 13 of these. And so this is the sequence that counts the directed animals of size n in general. The number of restricted hexagonal polyominoes. So this is basically the same thing, but on a hexagonal lattice instead of a square lattice. And the Reardon numbers count various lattice paths and other combinatorial objects. And in this paper, they show that there's a single set of integers that basically characterizes when these 3 sequences are even. And this set of integers, again, has to do with something to do with the base p, or the base 2 representation of n. And that's sort of preserved because then we're multiplying every number in here by 2 and by 4 and then subtracting 1 here. So what all these sequences have in common, the question is, can we obtain these results and prove them automatically instead of having these long case analyses that potentially take up many, many pages in a paper? And what all these sequences have in common is that they're algebraic, which means that if you take the generating series by putting the nth term of the sequence in front of x to the n, and you sum over all n, so you get this power series. This power series satisfies a polynomial equation. So for example, the power series whose nth coefficient is the nth Catalan number satisfies this polynomial over the rational numbers. And if you wanted to get a description of the Catalan numbers modulo a prime, it's very easy. All you have to do is you say, well, let me consider the generating series for the nth Catalan number modulo p or modulo 3. You just have to reduce the coefficients in this polynomial, modulo 3. And now you have a polynomial that this generating series satisfies over a finite field, over F3. So this is one possible answer. It's a little bit hard to get your your fingers on a particular term of the sequence. So if you wanted to compute the 100th term of the Catalan numbers modulo 3, from this, you would have to sort of, do some work. You'd have to expand the power series out or use the implicit function theorem or something. So it's not immediately direct, but it's still a finite description of the Catalan numbers mod 3. There's another description of the Catalan numbers modulo 3, and this is basically the main definition of the talk, which is that a sequence is P automatic if there's an automaton, which also this is a picture of an automaton that spits out the nth term when you feed in the base P digits of n. And in this talk, we're going to feed in the base P digits of n, starting with the least significant digit. That's just a convention. If you wanted to start with the most significant digit, you get the same class of sequences. So it doesn't really matter which reading direction you pick. But let's go through this automaton to get an idea of how it works. Basically, it's a simple model of a computer. So it's a computer that has finitely many states. Each of the states is represented by a vertex in this graph. This unlabeled arrow points to the initial state. So when we turn the computer on, we're in this state. And then we're going to start reading in base P digits of n. So for example, if we wanted to compute the nth Catalan number mod 3, we would write n in base P, which is 3 in this case. So the representation of 9 in base 3 is 100. And then we're going to start walking through this automaton, following the edges that are labeled with the base P digits of n. So we're going to read 001. We start here. We read a 0. So then we transition along this edge to this state. We read another 0. So that means we transition along this edge and we stay in this state. And then we read a 1. So we transition over here. And then since we're done reading the base 3 digits of n, we stop. And the output is the label of this state. So the output is 2. And so if this automaton computes the nth Catalan number mod 3, then what this is saying is that C of n is congruent to 2 mod 3. So are there any questions about this?
Just following the automaton.
Yeah.
So it goes the 0, 1, sends 1 to 1. The 0, 1 again, sends 1, the same node to 1. And then the 1 sends it to 2. And then you get
Yeah. So if you feed in other base P representations, each base P representation will give you one term of the sequence. So we say this is a 3 automatic sequence because we're reading numbers in base 3. So from every state, from every vertex in this graph, there have to be 3 arrows pointing out, 1 for each letter. And then the output states, the labels of the states are going to be remainders modulo 3. In this case, the set of values that the automaton outputs is the same as the digit set. But that doesn't necessarily need to be the case. So you could imagine reading numbers in base 3, but the output set can be some much larger set. If you were interested in the nth Catalan number modulo 9, for example, then the outputs might be 0 through 8 instead of 0, 1, and 2.
And so was it known? I mean, this automaton for Catalan, or it's just
so there's a general, I'll get to this. So basically we have these 2 representations, at least for the Catalan numbers mod 3, we have a polynomial representation for the power series, and we have this automaton representation. The polynomial is very easy to get from the polynomial over Q, whereas the automaton gives you more direct information about the nth value. And the very surprising fact, if you haven't seen this before, is that these 2 representations describe exactly the same class of sequences. So this is a theorem of Christol from 1979 and 1980 that says a sequence of elements in a finite field, it's more general than this, not just FP, it's any FQ, any finite field, is algebraic if and only if it is P automatic or Q automatic. So a natural question is, can you convert between these two representations for the same sequence? And the answer is yes. The proofs are constructive. So if you have a polynomial, you can build an automaton, and if you have an automaton, you can build a polynomial. And a natural question is, how do the sizes of these two representations depend on each other? So the automaton has a size measured in the number of states. So this automaton has 5 states. This polynomial also has a size, it has degree 2 in y and degree 1 in x. And so in this talk, we're going to be interested in starting with a polynomial of a certain size. How big is the automaton for the same sequence? The other direction, I don't think there's been much work on, going from the automaton to a polynomial. Okay. But first I want to go through this. So how do we tell whether a sequence is p-automatic? And this is going to be related to building the automaton. So if we take R to be a base p digit, there's this thing called the Cartier operator, which is a fancy name for a very simple operation. All it does is it picks out every pth term of the sequence that it operates on, starting with the rth term. So the lambda sub r of a sequence is s of pn plus r. And so what we do is we start with the initial sequence we're interested in. Maybe it's the Catalan numbers mod 3. And then what we'll do is iteratively apply all of the p Cartier operators to the original sequence. And we'll create one state in the automaton for each distinct sequence that we get. So let's go through an example. So this is for the Catalan numbers mod 3. The initial sequence, the sequence of Catalan numbers mod 3 begins like this. So what we'll do is we'll first apply each of the 3 Cartier operators, lambda 0, lambda 1, lambda 2, to this sequence and see what we get. So lambda 0 is every third term starting with the 0th term. So it'll look like 1, 2, 0, etc. That's a new sequence. That is not one of the sequences that we've already seen before. So that'll correspond to a new state in the automaton. When we apply lambda 1, this terms will be 1, 2, 0. So this sequence looks like it's the same as the sequence that we just saw. So that state will we won't create a new state for that sequence. That sequence will correspond to the same state in the automaton as this one. When we apply lambda 2, we get 2, 0, 2, etc. So that's a new sequence. That's not the original sequence or this one. So that'll also give us a new state in the automaton. So far our automaton looks like this. The initial state corresponds to the initial sequence. And then when we apply these Cartier operators, that the lambda 0 and lambda 1 both turned into the same state, and lambda 2 gave us a new state. And the output label for each state will be the initial term of the sequence. So this is labeled 2 because that's the first term here. This is labeled 1 because that's the first term here, and this is labeled 1 because this is the initial term of the sequence. And so we keep doing this to build the automaton. So we don't have output edges from these 2 states yet. So we need to apply the 3 Cartier operators to these 2 states.
Can you go back to a second?
Yeah.
How did you get the automaton from the sequences?
So each state will correspond to a sequence that we come up with, that we see.
Right.
So the initial state corresponds to the initial sequence. And then when we apply lambda 0, the digit here, the subscript, tells you what base p digit you're reading. When we applied these 2 Cartier operators, we got 2 sequences that were the same. So reading 0 or 1 in base 3 should take you to the same state. And when we looked at the second Cartier operator, this gave us a new sequence that we hadn't seen before. It's not one of the other 3. And so this will correspond to a new state in the automaton. So basically these states are representations of subsequences of the original sequence.
So is it obvious when you've got the state? and the same?
No, so like here, we're just looking at the first few terms, right? So this
Right.
is our best guess based on the first few terms. We could be wrong. So that's a problem with this method, is that we can't tell actually by looking at just the first 10 terms whether these sequences are actually the same. So yeah, we'll fix that in a few slides.
And does it keep going? Like where the 2-node goes?
Yeah, so here we're not done building the automaton yet. So now we have to apply these 3 Cartier operators also to this sequence and then to this sequence. And so if we keep going, so we take
Oh,
And is it
the,
also clear when we stop?
it'll be clear, we'll stop
we have
when,
everything
yeah, when
connected,
when
yeah.
everything's connected. Yeah, when we don't have any
mhm.
states without
But
arrows
then
going
you
out.
have to know when you're pointing, so once again, you have to know when you get the same sequence.
Yeah,
right?
exactly.
Because that sequence really corresponds to
Yeah.
that state. Okay.
Yeah, so at every step, when we compute one of these sequences, we have to compare it with our list of existing sequences and see whether it's on the list. So we have to keep going. This is applying lambda 0 to the lambda 0 state. This is, if we flip back to the previous slide, this looks like it's the same sequence. So that's not, oh yeah, so that's not a new sequence. Yeah, that's why there was a loop there. When we apply lambda 1 to lambda 0, here we do get a new sequence. So that's going to correspond to a new state. I couldn't get the states to appear live here, but we'll see the picture in a second. And when we apply lambda 2 to lambda 0, we get the 0 sequence, which we also haven't seen before. So that'll be a new state. And then we also have to apply the 3 Cartier operators to lambda 2, which was this state. And it turns out that we don't get any new sequences when we do that. So these are the 2 new sequences that we just found here and here. But we're still not done because we don't know where these point to. So then we have to apply the 3 Cartier operators again to those. And then it turns out we don't get any new states at that point. So this is the automaton we build. This was worked out by Eilenberg in the 70s. So this is really a representation of, this automaton will give you the sequence. So there's a bijection between states in the automaton and subsequences that can be obtained in this way. But this is the point that Sylvia brought up. We've been cheating this whole time because we've just been looking at the first few terms, and that's not really reliable in terms of telling whether 2 sequences are really the same. So this is just a guess at this point. We need a better way to represent subsequences, and that will be as diagonals of rational functions. And that'll give us a finite representation. So how does that work? So we take this a polynomial for the Catalan numbers. So this is the generating series for the Catalan numbers. I've chopped off the 0 term here. So this is a slightly different polynomial than we saw earlier. The reason I chopped off the 0 term is because to convert an algebraic power series to the diagonal of a rational function, there's a condition where you need the constant term to be 0. So this is a result of Furstenberg in the 60s. This is the formula. If you have a polynomial P, so this comes from this polynomial that your algebraic series satisfies, then you can turn it into the diagonal of a rational bivariate series using this formula. So you take the derivative of the polynomial with respect to y, and you plug in xy instead of x, and you plug in xy instead of x in the original polynomial. This y down here is because it turns out that because we've required the constant term of the series to be 0, like it turns out that all of the monomials here are divisible by y, so you can get rid of a y from them. And then there's an extra y up here. For this polynomial, for the Catalan numbers, you get this bivariate rational series. And if you reduce this mod 3, you get this. And so what this is claiming, using this construction of Furstenberg, is that the series of Catalan numbers modulo 3 is the diagonal terms along this bivariate rational function. So I don't know if this looks familiar. 0, this used to be a 1, but we turned it into a 0 to use Furstenberg. So now this is 0, 1, 2, 2, 2, 0 instead of 1, 1, 2, 2, 2, 0. And it turns out that we can apply Cartier operators to sequences in this form, diagonals of rational functions, in a way that we can represent the states in a finite manner. So what we've done is we've embedded a general algebraic sequence as diagonal of a rational series. This Q, this is going to be the denominator. S0 will be the initial state, and then this is what's going to replace the big lambda Cartier operators. These are like little cousins of the Cartier operators. Now they're in two variables because now these polynomials are polynomials in x and y. And so I'm skipping some details here, but this turns out to be the right operator to use. So we'll start with we're going to represent states not by the first few terms of a subsequence now, but by a bivariate polynomial. So this will be the initial state when we apply this function to it, lambda 0, 0. So we multiply by q to the p minus 1, and then take the old Cartier operator where we take every. This is a slight change in notation here. This is a polynomial now. So what does it mean to apply a Cartier operator to a polynomial? You treat it as a sequence of coefficients. So this will pick out all of the coefficients, all the terms in the polynomial whose x exponent is congruent to r mod p and whose y exponent is congruent to r mod p. But you do the same process. So you apply these three Cartier operators to this initial polynomial. Turns out you get three new polynomials, and then you have to apply these Cartier operators to them, and you build this automaton in that way, where now each state is represented by a polynomial rather than the first few terms of a sequence.
Q is the denominator.
And Q is the denominator.
P is 3, I guess.
Yeah, so P is still 3. So there are these three Cartier operators for 0, 1, and 2.
So how do you see that? Sorry, how do you see that? Still taking this in, that 0 goes to 0 in the first arrow.
So this is the initial state. So the representation of this state is this numerator polynomial. And then when you apply the 0th new Cartier operator to this polynomial, you get a new polynomial. This polynomial will be the representation of this state. When you apply 1, you get a different polynomial. So that'll be the representation of this state. And when you apply 2, you get yet another polynomial. So you get a representation of this state. So if you remember before, 0 and 1 pointed to the same state. Right. So they don't point to the same state anymore. And that's because if you've turned a one-dimensional sequence into the diagonal of a rational function, there are potentially many, many rational functions that have the same diagonal, right? Because there's all sorts of information off the diagonal that you're throwing away. So this automaton may have extra states. It may not be minimal. It may have extra states relative to the other method, because it could happen that these polynomials that are really numerators of rational functions, all with denominator q, have extra information in them that we don't actually need.
So I'm still not clear how you're getting the names of each state. So the 0, 0 and 2, 1. So from 0 you get a 0 and you're going to the 0 thing, and that's because what coefficient is it? 0? Yeah,
so these output labels is what you're saying, right?
Yeah.
Like, why is this a 0? So what you'd have to do is let's look at the initial state. So why is this a 0? So you'd have to take this rational function, and you'd want the constant, or you'd expand it as a power series in x and y, and you look at the constant term.
Okay, the constant term.
The constant term is 0 because there's a y up here everywhere.
Just of the numerator.
No, you'd have to expand. Yeah, you'd have to expand the whole rational expression. So if I go back to the previous slide, like the initial, it's this term you would pick out for the label of each state. So yeah, so really these are polynomial representations, but we have to remember that they're really like numerators. The nice thing is that all of the denominators are q. So I skipped an explanation of why this is the right function, but this is the right
Okay, so
function.
For this other one, for the 0, 0, what we take is that as the numerator and then expand it.
Yeah, exactly.
in-
So
in
you,
the first term in the diagonal.
yeah,
Okay.
put each of these over q, expand it, and then take the constant term. Other questions? Okay, so that is all mod p. And there's a result that says you can also do this modulo p to alpha. I'm not going to go through the details, but it's a variant of what we just showed. So this is a result of Denef and Lipschitz from 1987. They actually gave two methods in their paper. And the second one, which is kind of buried in a remark at the end, is it turned out to be much more useful computationally. So that's the one we're using here. And it says that if you have a bivariate, actually a rational expression in any number of variables, as long as the constant term of the denominator is invertible mod p, because you need to be able to invert it into to get a power series, then when you take the diagonal terms and reduce them modulo a prime power, you get a p automatic sequence where this prime is the same prime as the prime that you're reducing modulo a power of. And this works more generally. You can think of this as the integers, but it also works more generally in the p-adic integers, for those of you familiar with that. And this let us compute, this is still work from 2015 that I did with Reem. This lets us compute a lot of information about combinatorial sequences. So once you have an automaton, then you can tell easily whether there are any forbidden residues, like the Catalan numbers are never congruent to 3 mod 4. It lets you compute the limiting distribution of the residues. For example, maybe 1/3 of the Catalan numbers are 2 mod 3 or 2 mod 4 or something like that. If that limit exists, which it doesn't have to, it lets you decide whether the sequence is eventually periodic. And there were some open questions that we were able to answer by just running a decision procedure to test whether a sequence is eventually periodic or not. And many other questions that are known to be decidable because automata have been studied by computer scientists since the 60s or so. Okay, so let's go back to the Catalan numbers modulo 8 and modulo 16. So here are the automata for them. This is a theorem that I hadn't mentioned yet, that no Catalan number is congruent to 9 mod 16. And their proof of this was, you have this long case analysis to determine what the Catalan numbers are modulo 16, and you show that there's no 9 case. Our proof is you just compute the automaton. So this is completely automatic now. We have code for it. So you just compute this automaton and you just check that there's no state that outputs 16. So if there's no state that outputs 16, then no Catalan number can be congruent to, that outputs 9. There's no state that outputs 9, so no Catalan number can be congruent to 9 mod 16. And here are several other forbidden residues that we found. At some point, you have to ask yourself, like, is it interesting that no Catalan number is congruent to 106 modulo 128? Probably not, right? That's probably just a coincidence or something. But maybe a better question is, as you keep raising the power of 2, what density of residues is attained by the Catalan numbers? And so modulo 2 to the 9th, only about 35% of the residues modulo 2 to the 9 are actually attained by the Catalan numbers. And we don't know whether this tends to 0 or whether it tends to some positive number. So this is an open question.
Is it known that the other residues are hit? Like mod 32?
Yes,
Like-
so
You computed the automata.
we computed the automata. So I'm not, if no Catalan number is congruent to 17 mod 32, that also knocks out 2 residues mod 64. So I'm not duplicating those here. Like no Catalan number is congruent to 17 or 17 plus 32, whatever that is. So these are just like the new ones that appear. So yeah, so it looks like all the other ones appear, but a lot of the others are knocked out by smaller forbidden residues also. All right, so let's get back to the question of how big can the automaton be, right? So we start with a polynomial representation of a sequence, and we're computing an automaton for a sequence, for the sequence modulo a power of a prime. For the Catalan numbers, modulo 2 to the alpha. For alpha 1 through 9, here's the size of the automaton that the construction gives. So this is the unminimized automaton. The minimal automaton will, of course, be smaller. And this is basically an exponentially growing sequence. So you can fit a curve to it. It's about 2 to the alpha. And kind of what we see when we do these experiments is that this 2 is probably this 2. It's probably something like p to the alpha is what we expect from doing all these experiments. But the bad thing is that the upper bound that the construction gives is doubly exponential. So if h is the x degree of p, so this is called the height, and d is the y degree of p, this is p, the polynomial that represents the sequence, the algebraic sequence, then the upper bound that we get from the construction is p to the 2 alpha minus 1. So it's really bad. So just to give you an example of how bad this is, for the Catalan numbers mod 9, this is the polynomial for the Catalan numbers. So it has height 1, x degree 1, and degree 2. This is the bound that the construction gives, whereas the actual size is at most 2,500. So this is way larger than what we're seeing in practice. So why is this bound so large? And so now we're transitioning into the stuff that we're working on currently. The simpler setting is to go back to not modulo p to the alpha, but just mod p. And so this corresponds to the finite field case. And this is a theorem from 2017 by Andrew Bridy that says if the minimal polynomial p has height h and degree d, then the minimal automaton for the sequence has size basically p to the hd. So this is the right bound according to the experiments. And there's this little o of 1 term. This goes to 0 if you increase any of the 3 parameters. And so this seems to be really what we're getting. So is this bound sharp? We suspect it is sharp. We computed a lot of, maybe you can tell, we spent a lot of time computing automata and playing around with them. This is a table for various heights and degrees. This is for p equals 2, and this is for p equals 3. This is an example of a polynomial that gives you the maximal automaton size for that height and degree. So there may be others, but we just picked one. This is the automaton size that you get, and this is p to the hd. So you can tell that the automaton size is slightly larger than p to the hd, and so you need that little o of 1 term. That little o of 1 term you can't just get rid of it. Like there is something there, but it's the same order of magnitude, and so this is why we think the bound is the right bound asymptotically.
What's the height again?
The height is the x degree of the polynomial, and the degree is the y degree. And this last column, so Bridy's result was an asymptotic result, because it has this little 1 term. Since I'm computer oriented, I wanted to know, like, okay, well, give me an exact upper bound. I want to know, like, not just asymptotically, but is there an exact upper bound? So this last column is an exact upper bound that I'll show on the next slide, and that is, it's a little bit larger than the automaton size, but again, it's fairly close. One thing that I didn't particularly love about Bridy's bound was that the tools used in his proof came from algebraic geometry, which I'm not that familiar with. And it sort of felt morally like, to understand automata, we shouldn't need tools from algebraic geometry. If you know algebraic geometry, then you're fine to use, then great. You're perfectly happy using tools from algebraic geometry. But if you're not, then it's a little bit, you want something that you understand better. And so this is the bound from the previous slide. This is our result from last year. that the minimal automaton has size at most this. So this is the p to the hd. So this agrees with Bridy's bound. And these are very small log terms. This is like the second order term. So it's p to the h minus 1 d minus 1 times some stuff. This stuff is a product of Landau functions. What is the Landau function? So L of 5, to compute it, you look at all the integer partitions of 5. So here are the integer partitions of 5. You take the LCM of the parts of each partition, and then you take the maximum LCM that appears. So here the LCM is 5, here the LCM is 4, here the LCM is 6, and this turns out to be the largest LCM that you see among an integer partition of 5. So I'm not going to say anything about this proof other than just explain where this Landau function comes from, because it's kind of neat. Basically, we're dealing with bivariate polynomials. Each state is represented by a polynomial in x and y. It turns out that in some regions you can project to univariate polynomials. And so what we end up getting is 3 univariate polynomials arise. That's why there are 3 terms right here. So their degrees are going to be bounded by h, d, and d, the height and the degree. And it turns out that the factorization of these polynomials, mod p, gives you some information about the size of an orbit. So the number of states that you're going to see when you keep applying one of these Cartier operators. So if the period length of this orbit is the least common multiple of the degrees, and so in the worst case, the biggest this could be is when these exponents are all 1. And so now what are you interested in? You're interested in LCM of a bunch of numbers that add up to the degree of this thing. So this is where the integer partitions come from. Like we have some polynomial, its factorization into irreducibles is going to correspond to some integer partition, and the LCM of that integer partition is going to give us information about how big this orbit size is.
Sorry, I got lost a little bit.
Yeah.
Capital R is just the.
Yeah, so this is going to be one of 3 univariate polynomials that arise.
Okay, so there's an original.
Yeah, the original
series.
Yeah, the original polynomial p is a bivariate polynomial. These 3 R polynomials are related to p by projecting in various one-dimensional, projections. So the proof is quite technical. The paper is on the archive if you want to take a look, but I don't want to spend any more time talking about it here. We were interested in automata modulo p to the alpha. So this was for the modulo p case, and it also works in a general finite field. But we wanted to know, really, the goal was to understand automata modulo p to the alpha. And it turns out that all of this machinery we were able to adapt to work modulo p to the alpha. The thing is that we still got a doubly exponential bound when we did that. So there's an extra step, which is to really understand more about the structure of these automata. So these are the Catalan numbers, again, modulo 8 and 16 and other powers of 2. And each one of these automata has the information of the previous automata in them, right? If you take the automaton modulo 16 and reduce the outputs mod 8 and minimize, you should get this automaton. So you can think about going the other direction, increasing the power of 2, and you can set up an idea of an inverse limit, right? So these automata should have an inverse limit, which you could call a profinite automaton. And the question is, can you describe states in this profinite automaton in some way? And we tried this many years ago, and it didn't work. The recent realization, though, is that there is some structure. We did find some structure in the states, and so this is kind of a technical theorem, so you can ignore it if you want. But the point is that that for a sequence modulo p to the alpha, every state in the automatons, these are bivariate polynomials, has this form. So q is the original denominator from the rational function. and the powers of P increase. And so basically, if you want to reduce modulo a smaller power of P, you can just get rid of some of these terms. So it turns out that these TIs, these are polynomials not with coefficients modulo P to the alpha, but just with coefficients modulo P. And so this sort of contains all the information about what happens modulo smaller powers of P in addition to the current power of P.
And so the N is it any?
Yeah, so this is the Catalan numbers or some other algebraic sequence, or really, you can really start with the diagonal of a rational power series. You don't even have to start with an algebraic sequence. So I'll just say that if you factor out this power of Q, you get this representation, and this kind of looks like a p-adic integer representation. If you imagine alpha going to infinity, you're going to get more and more terms here. So it's not, the weird thing is that it's not P to the I, it's P over Q to the I. So it's some weird thing that that we don't really know what to make of it, but this seems to be what happens. But anyway, this is finally the thing that gets us a singly exponential bound. So this is the bound that we get, where P to the alpha is the prime power, and H and D are the height and the degree. And sure enough, when you plug in alpha equals 1 into this, we recover Bridy's bound for the finite field case. So the next two slides are references, so I'll stop there, and if there are any questions, I'd be happy to answer them. Thanks.
That's the Catalan, I don't remember this. The Catalan numbers satisfy some kind of recurrence relation.
Yes, yeah.
Whatever it is, but
yeah,
but
yeah, I don't remember what it is,
is
but
there
they do.
some like characterization of algebraic power series? I don't know. It's just like a general in terms of like if there's some kind of version of a recurrence relation.
So if you have a recurrence relation where the coefficients are constant, that corresponds to rational power series. If you have a recurrence relation where the coefficients are polynomials in N, this corresponds to what's called d-finite power series. So they satisfy linear differential equations, basically. And algebraic sequences are a subset of those. So yes, but indirectly.
Oh, that's really interesting.
Yeah.
So you said that, or maybe I read in your paper that many algebra methods are used. What sort of linear algebra methods?
So it turns out that this function, so this takes a polynomial in X and Y and spits out another polynomial in X and Y. This is actually a linear function if you take the coefficients of the polynomial and consider them as a vector. And so what we're using is when we project to these one-dimensional polynomials, I don't even know if there's a theorem about it, but basically there's a way to get information. We're applying all these Cartier operators to this large set of polynomials, and on 3 slices of this space, you can forget about what's happening on the other space, on the other part of the space. And so it's basically, we're using the fact that you can project.
Like
There's some orthogonal projection that gets us down from P to the H plus 1D down to P to the HD or something like that. Yeah.
Thank you.
Yeah, sure.
You had some theorem that like towards the end that you said works for the diagonal of any power series. Maybe this one, or the one you just.
This one?
I think you said.
Oh yeah. So let me go back to the construction. So we start with an algebraic power series, and this was the motivation because a lot of these sequences that come up in combinatorics are algebraic. But the first thing we do is, if I can find it, we use Furstenberg's result to turn it into the diagonal of a rational power series. So suppose you didn't have an algebraic sequence. Suppose you started with a diagonal of a rational power series. That's perfectly fine. We can just use our methodology starting from that step. So all this stuff works more generally for diagonals of rational power series.
But for the P, I'm a little confused, but like for the P automata part,
Yeah. Oh, maybe it's this theorem. So this theorem of Denef and Lipschitz just starts with a diagonal of a rational power series
okay.
and says that when you reduce it mod p to the alpha, it's P automatic.
So that's sort of a generalization or something different than the Christol.
Yeah,
Result.
right. Which tells you how to get a diagonal of a rational power
Oh.
series. So yeah, we're using
I see.
we're using Furstenberg to turn an algebraic power series into the diagonal of a rational power series. And then we're using this result to generate the automaton.
And then my one other who knows what the answer is question, but it's like, so you have this result that there are P automata for algebraic power series, but those satisfy, you said those are a subset of the ones that satisfy differential equations. So maybe there's some sort of like what corresponds to the ones with different equations.
Yeah, that's a great question. Yeah.
Just general.
Yeah, I think when you would take a general sequence whose generating function satisfies a differential equation and you reduce mod p, I don't think it's going to be P automatic in general.
Yeah. Maybe there's something else.
Yeah, exactly.
So the question, like you answered a lot of found a way to deal with the powers of two, right? That we discovered before, and so you try to do it with a 3 now, just to see like how beyond.
Yeah, so since powers of p grow exponentially, it was easier to get. It's much easier if the prime is small to compute large powers of 2, right? So 2 to the 9th is only 512, but 3 to the 9th is something much larger. So to compute these automata, it's actually quite a computation. Where's an example? So there's 2,400 states in this automaton, which isn't a lot, except that the states have really large representations. So each state is represented by a bivariate polynomial, but these polynomials are really, really huge. So the computer, it's not so much a matter of time, it's a matter of space on your computer because you're dealing with these really large polynomials. There's some hope that this theorem at the end, now that we understand the structure of these states better, there's a hope that we can go back and find a much better algorithm that will use the structure of the states. We haven't done that yet, but it's on the list of things to do.
Matryoshka, right?
Right.
Matryoshkas, right, separate, and then you're kind of packing them now.
Right, exactly.
Inside one matryoshka,
Right.
so like a small
Right.
right? Use somehow, right?
Yep.